All right, now we need to talk about our very last definitions of acids and bases. We've met Arrhenius acids and bases, we've met Bronsted-Lowry. Now we want to talk about Lewis acids and bases. From an organic perspective, they're a very important set of definitions. From my way of thinking, man, I wish I'd been born about 100 years ago and I could have gotten away with the world's easiest PhD dissertation. All right. We defined Bronsted-Lowry bases as a proton acceptor. Well, in order to accept a proton, you have to have a lone pair of electrons. Right? We look at the lowest structure of ammonia, and it functions as a base because it has two lone pairs of electrons to donate to a proton. What the Lewis definition of acids and base does is it takes the definitions of acids and bases from the electron viewpoint as opposed to the proton viewpoint. It defines a base not as a proton acceptor, but as an electron pair donor. It defines an acid not as a proton, but as a electron pair acceptor. It really turns that definition of acid bases kind of on its head, and it broadens it a great deal. Just like Bronsted-Lowry broadened the Arrhenius definitions, Lewis broadens Bronsted-Lowry. One thing to keep in mind as we're moving along here, as a general rule, you have let's see here. You have escorts. You have Ford Escorts. That's a type of compact car. All Ford Escorts are cars. And all cars are vehicles. Arrhenius acids, all Arrhenius acids are going to be Bronsted-Lowry acids. All Bronsted-Lowry acids are going to be Lewis acids. But it doesn't work the other way, right? It's a one-way street. All vehicles are not cars. All Lewis acids are not going to be Bronsted-Lowry acids. All cars are not Ford Escorts. All Bronsted-Lowry acids are not Arrhenius acids. So beware of that dichotomy, and I'll hit on it again as we move along. A Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. The big place where we see Lewis acids the Lewis acid definition broadening things is in the concept of the metal ion. We talked about metal ions functioning in an acid-base context previously. Let's look at what they're doing. When you place a metal ion in water, these lonely electrons on the water find that positive charge irresistible, and therefore the water donates a pair of electrons to the aluminum. Since the water is donating electrons, that makes it a Lewis base. Since the aluminum is accepting the electrons, that makes it a Lewis acid. Notice how the other side of a Lewis acid equation, a Lewis acid base equation, looks. Instead of having hydroxide or hydronium over here, we have this interesting compound. We have one product because we're forming a coordinate covalent bond. That's another thing to realize. You're donating a pair of electrons, right? A Lewis acid-base reaction forms a covalent bond. The product of the addition of a Lewis acid plus a Lewis base is given a special name. It's called an adduct. I'd make a joke about the name being adduct, but I've already quacked myself up enough today, and I don't want to run afoul of anything I might talk about, because after all, we are talking about a adduct. All right, I know it's a stretch. Bear with me. End of the semester. All right. Couple hints to keep in mind when you're classifying things as Lewis acids and bases. Whenever you see a metal cation, in other words, a metal with a positive charge, it's going to be a Lewis acid. Nitrogen loves to function as a Lewis base. Why? Because in a lot of structures, nitrogen is bound to three things with a lone pair of electrons sticking out there, ready and waiting to be donated. In other words, ready and waiting to be a Lewis base. Oxoanions also like to be Lewis bases. Why? Because you've got that chlorine and you've got all those oxygens, and all those oxygens have all those electrons sticking out, priming and ready and waiting to go. Anions also like to be Lewis bases. Why? Well, an anion is gained electrons, which means it usually has at least one complete set of valence electrons, if not several. Well, it usually has at least two lone pairs of electrons, if not more. So anions also generally like to be Lewis bases. Take a look at another example of a reaction. We have ammonia. It has a lone pair of electrons that it's donating to copper. Since the nitrogen is donating in a pair of electrons, it's a Lewis base. The copper 2 ions accepting the lone pair of electrons, so they're a Lewis acid. They're forming a new compound, which we refer to as a adduct. Quack, quack. Write down goose. Write down goose. G-O-S-S-E. Write down goose. Here is an example of where Lewis acids really begin to radically diverge from Bronsted-Lowry or from Arrhenius. If we look at this reaction, we don't see any protons moving about. What we see is we see water with a pair of electrons donating them to a sulfur in a sulfur trioxide. Because the water's donating a pair of electrons, it's a Lewis base. Because this is accepting a pair of electrons, it's a Lewis acid. We can also see how one Lewis base reaction can beget others. Because this oxygen donated a pair of electrons, this sulfur sent electrons back to the oxygen. This oxygen now has 3 lone pairs of electrons, and it's more than willing to share. So here this oxygen is donating a pair of electrons to the hydrogen. So this oxygen right here is functioning as a Lewis base. That hydrogen's functioning as a Lewis acid, accepting them. And it's sending its electrons back to the oxygen. These little electron arrows are going to become more important as you go on in chemistry. A lot of what you do in organic chemistry you'll explain by pushing electrons, is what the term's always referred to as as pushing electrons from one atom to the other. But because that oxygen donates the electrons to hydrogen, that hydrogen gives its electron to the oxygen, and you wind up with sulfuric acid. All right, for each of the following reactions, identify the Lewis acid and the Lewis base. All right, so we have the reaction of carbon dioxide with hydroxide to form the bicarbonate ion. It's easier to spot very often the Lewis base. We see right away that we have a negative charge, a clue that this has a lone pair of electrons. If we were to draw out the Lewis structure, which is really the best way to answer these, if you want to be 100% sure, you need to sketch your Lewis structures. That's your Lewis structure for your hydroxide. Carbon dioxide, on the other hand, it doesn't really have any extra electrons. Matter of fact, it's got a double bond it's looking to get rid of. So you have some lone electrons on that oxygen that are ready to come in and replace that double bond on the carbon. And the carbon would more than likely send it back to the oxygen. But your clue in order to answer this question is really, hey, I see an anion. Anions like to be Lewis bases. I see an anion, so I know I've got a Lewis base. By default, then, this must be my Lewis acid. I have no idea why, other than the fact that I've identified that as my Lewis base. Well, I do have an idea why, and we showed the Lewis structure there. But our clue in terms of answering this question on an exam or homework is, hey, I have an anion, so I must have some lone electrons to give. Let's take a look at another one. We have boron hydroxide plus hydroxide yields this fun guy. Once again, we see an anion, so that's going to be our Lewis base because it'll have extra electrons to give. This is actually more helpful. Boron's a metal. And when you have a compound with a metal like that, that's generally a big clue that it's going to be a Lewis acid. So because you see that metal, it's likely to be your Lewis acid. If you have an anion, that's going to be your Lewis base. All right, we keep going here. This one's about as easy as you can get on an exam. You have cyanide, and you have iron 3 forming a complex or forming an adduct. Once again, you have an anion, so that's a good clue that it's going to be your Lewis base. You have a metal, and we know metals love to be Lewis acids because they love to accept those empty pairs of electrons. So those are our clues that let us do the determinations. And that's all you're really going to be doing with this chapter. Beep.